Hello everyone, this is Kaelyn. Today I'll be explaining a two-layer perceptron and train it on a regression curve, concentric rings, and 3 Gaussian blobs. Here's the main structure of an MLP. The input layer, the hidden layer, and the output layer. Each circle represents a neuron, and every connection is a weight that the network learns. First, the input data is passed through a linear transformation. This combines the inputs with their weights and biases. Next, we apply the ReLU activation function, which keeps positive values and sets negative ones to 0, adding nonlinearity. The transformed outputs then flow to the next layer. Finally, if this is a classification task, we apply softmax to turn raw scores into probabilities. For regression, we simply use Z2 directly as our predicted value. Together, these steps make up the forward pass of an MLP. To make the network learn, we use forward propagation, loss computation, and back propagation. The forward pass computes predictions from the inputs. The loss function measures how far the predictions are from the true outputs. For regression, mean squared error, and for classification, cross entropy loss. Back propagation calculates gradients, basically how much each weight contributed to the error, and then we update the weight using the gradient descent. This process repeats over many epochs, and the loss gradually decreases as the model improves. Our first data set is synthetic regression. Our input is one-dimensional values between -2 and 2, and our target function is a piecewise linear curve made from two ReLU-like shapes. The goal is to teach the MLP to fit a continuous curve, and the model is regression. You can see after training, the network learns to approximate the curve and smooth it out. For the second data set, we're using concentric rings. The input is 2D coordinates forming two noisy circular rings, an inner and outer one. The labels are 0 for inner and 1 for outer, and the mode is classification. The third data set is 3 blobs. We have the input of 2D points from 3 Gaussian clusters, each centered at a different location. The labels are 0, 1, and 2 for each cluster. The mode is classification. The MLP learns to separate the 3 regions into space, creating 3 clusters that match the blob structure.
This is Aqib Haider, and I will be presenting part 2 of the Lab 7. So this is our Jupyter notebook for part 2, in which we simply develop a CNN network, convolutional neural network, and just test it on our CPU to see how a convolutional neural network is written. So we import these libraries: NumPy, OS for joining the path, image for image processing, and matplot for plotting. And here we define loading of the data. We define two lists, and we enumerate in cats and dogs and join the path because cats and dogs are the subfolder. And for every image in that path in cats or dogs, we open the image, convert it into RGB, and resize to 64. And then we normalize it by dividing by 255 and append it to X, and we append the label as 0 or 1 into the Y list, and then return the NumPy array of X and Y. So this is the definition, and here we use it to load the training set, and we just run it. So here it is running, and then we'll shuffle it and print to see that they are fairly shuffled. After that, we again load the test data using x2, y2, and again shuffle it, and then test the shape, whatever it is. Later, these are the definitions. These are rectilinear unit, which basically returns maximum of 0, or x basically returns x if it is positive, or 0 if it is negative. This is the differential of ReLU. This basically is, if it is negative, it is 0. If it is positive, it is 1. This is the MSE mean square error loss and mean square error gradient. These are the convolutional filters, 3 by 3 of 3 channels, and weights, randomly initialized convolutional filter and weights. And this is 31 by 31 because after pooling it will be 31, and weight numpy also. Let's see if it is loaded. So yes, here it is loaded. Then again we run it. Okay, so here we can see the labels are shuffled. Again we load the test data. While it is loading, we can go through further in the code. This is the convolution we have defined. We load the shape and the kernel, shape of the image and shape of the kernel, and define an out numpy as in and initialize it with 0. So this is basically the this is assuming keeping the out shape to be the same. So h will be 64, kh will be 3. So this will be 64 minus 3 plus 1, which will be 64 minus 2, that is 62. So eventually we will this will do the convolution and we will return out, which will be 62 by 62. And then here we will pool it by a factor of 2 by 2. So again we will divide it by 2 and return the maximum of that region. So this pool will be 31 by 31 because 62 divided by 2 is 31. And here is the feed forward function, which takes in this global convolution filters and does the convolution, does the rectilinear unit, basically introduces the non-linearity in the convolution, pools it, flattens it, and then gives out the final scalar value, which is just one value, and returns all of it: fc out, flat, pooled, and ReLU out. And then we have the training loop in which we set up all the we use all the defined functions. We set the learning rate as 1 by 1000. We take 10 epochs. We store the loss here. We note the time, and for each epoch we set the loss 0, and then start training. We load the image for all images in xtrain, and then we predict the output label by ypred, predict the loss using MSE loss, add it, and calculate the gradient. And here we basically the calculate the gradient of weights and biases and update it by after multiplying with learning rate. And for each epoch we calculate the total loss dividing by the length of the training data set and append it to the loss loss list. And finally we print the total time taken. So by now the test data might have been loaded. Yes, it is loaded. And again we shuffle it and we just see the shape of test. So basically there are 2023 elements in test. So 64 by 64 into 3 for 3 channels. Let's just see what is the number of samples in train. It should be 8005. Yes, it is 8005. Let's just see quickly. We run it. So now we will start the training. We just add one line, print starting training. So training has started, and it will take quite a while to train the images. So I will pause the video here and then uh, we can resume when it is done. Okay, so we are done with the training and we could see there are 10 epochs, and with each epoch the loss decreases and starts from 0.2543, ends at 0.2368, and it roughly takes 4600 seconds, which is roughly 1 hour 20 minutes approximately. And now we will test our train model on the test set that we have got in this block, and then we'll do the same on our training block. So basically we have a list that says test score. It's an empty list and it appends the predicted y, and later we're going to use that in confusion matrix display. So I'll just pause it till both of them are done completely. Okay, so we have the test accuracy, which is around 58%. Now we will run the same on training data set. Okay, so we have the training accuracy also, which is around 61%. So test accuracy 58%, training 61%. And then we have the loss curve. We plot the loss over here, the loss that we calculated. Let's just plot it. So this is the loss, basically goes from 0.255 to 0.2375 over the epochs. Now we have the code for confusion matrices. For that, we just convert to binary and plot the matrices. So here's the confusion matrix for the training and test. We can see. So we see we have roughly more wrongs, more rights than wrongs. Both here and here we have 2564 and 2335 rights, and 1670 plus 1436 as wrongs. Here also greater rights than wrongs. And then we have the logic distribution. So the blue ones are training and the orange ones are test predictions with the 0.5 as the decision threshold. So that will be all for part 2. Thank you.
My name is Ravi, and this is E542 Lab 7 Artificial Neural Network tutorial. It takes the lab is divided into 3 parts. The first part is multi-layered perceptron for regression and classification. The second part is convolution neural network for binary image classification using CPUs. The third part is convolution neural networks for binary image classification using GPUs. And I'll be talking about the third part. Before I dive into the demonstration and the code, I'd like to briefly show what a convolution neural network architecture is. This is a popular neural network architecture called AlexNet. So we have the input image, which is 227 cross 227 in resolution. And we have the 3 input channels, the red, green, and blue channel. We have the convolution kernels that perform convolution on this image, and we reduce the dimension as we go deep into the neural network. Here we can see that 227 cross 227 is reduced into 6 cross 6, and we can see the number of channels has increased. This represents that the model is trying to learn the features of the image, and the 256 channel represent the number of features it is trying to learn. These are then converted into a fully connected layer. The fully connected layer here represents the artificial neural network. Then we have the final output probabilities, which show the prediction of classes of the input image. Once we have the final output probabilities, we find the loss between the predicted and the ground truth class of the input image, and we train the neural network using gradient descent and using backpropagation. both the weights of the fully connected layer and the convolution kernels are updated during backpropagation. Here, this is a representation of what convolution is. This is the input image, and we have the convolution kernel. This kernel represents the edge detection, the vertical edge detection, because we have values 1 over here in the columns, uh, 1 and -1 in the columns. So this is nothing but multiply and accumulate, and we can see that convolution kernel is striding across the over the image, and the input image is reduced in dimension, and we get the output image. Our neural network model is inspiration from the AlexNet model. We have 4 hidden layers. We have the input size is 64 cross 64, and we send in n images in each batch, and we have the 3 channels RGB. The block 1 is the convolution block, input image, and the 3 channels are converted into 16 channels. The convolution kernel size is kept 3. Uh, the stride is kept 1. The padding is kept 1. This convolution output is then sent into the ReLU function, and we then do max pooling to reduce the dimension, and we get the n cross 16 cross 32 cross 32 image. Now we perform second convolution, which is similar. Then we do dropout. Dropout is used to improve the generalizing capability of the model. Then we have the final fully connected dimensions as n cross 8192, and 8192 here represents the number of neurons that we have. We have the second fully connected layer as 128, and we get the final output logit. This output logit is the probability of the class being in class 1 or class 0. So since this is a binary classification, we would get the probabilities between 0 and 1, and we threshold based on the final class that we want to represent the image for. For example, classifying dogs and cats, and for dogs, the threshold probability should be greater than 0.5, and that's how we train the model for classifying it to dog or cat. The loss function that we are using is BC with logit loss. I'll talk about it in a moment in the code. And the optimizer function that we are using is Adam optimizer with a learning rate of 10 raised to minus 3. I'll hop onto the code now. So you can find the dataset on Kaggle. The dataset is named cat and dog. The dataset provides us with the training and the testing split. First, we check for the CUDA, the GPU, if it's available or not. Then we get the data from the Kaggle dataset library. So we have the transform object, which reduces the input image dimension to 64 for 4 cross 64. For this is across all images for uniformity in training, and we transform it to tensor, which contains values between 0 and 1, and the shape is channel cross height cross width. The number of channel is 3 over here. We load the training set and the testing set. We kept the number of workers 4 because we have a CPU with 4 cores. So for faster loading, we have kept the number of workers to 4. We have training 8005 training images and 2023 testing images. Here we have the model class. It takes in the input image n cross 3 cross 64 cross 64 and reduces the dimension, and this is the forward pass of the model, and we create an object model for the class, and we send it to device, as in we send the model, we place the model onto the device. Device here is the GPU P100 that we are using. This is the loss criterion that we are utilizing for our training. So it utilizes both the advantage of binary cross entropy and sigmoid. So this is the formula for binary cross entropy, and this is the sigmoid um, output of the logic. We train the model for 10 epochs, and we call the loop for the loop to train the model for the number of epochs. Then we call the model the object of the model to train the model. And we set the system baselines. We ensure that the CUDA timing is synchronized. Within each epoch, we iterate over the train loader. We convert the images and labels to the device we send, and then we send it to the GPU. The labels are converted to float column vectors n cross 1, n being the number of images that we send in. We zero out the gradients before the training. We forward pass through the images. Uh, uh, we forward pass the images through the model to get the logits. Then we calculate the loss using the criterion that I showed earlier. This is BC with logits, and then this is the main training step, which is we do backpropagation to update the weights of the models. We cause loss backward for the backward pass, and we update the weights using optimizer.step. We calculate the efficient batch size and update the total loss, and then update the total number of samples list. After the epoch is completed, we synchronize the GPU to ensure all operations are completed. Then we synchronize the GPU to ensure all operations are completed, and we calculate the average loss and throughput. We then calculate the GPU stats, the memory used, uh, and the percentage utilization of the GPU. Here we can see that the loss throughout the epochs reduces, and the training is successful in reducing the loss. We can see that we can see time for each epoch to run, the throughput, uh, as in how many images were processed per second, and the GPU percentage utilization, and the memory utilization of the VRAM of the GPU. Here we also calculate the CPU utilization and the RAM usage. After training the model, we finally evaluate the model on the test set using the test loader. We call the torch no grad function, which is used to disable the gradient calculations because we would be forward passing all of the images, and we don't want the model to learn on the test set. After the model is evaluated, we call the model evaluation function, and after the model is evaluated, we synchronize the GPU to ensure all operations are completed. We iterate over the test loader and convert the images and labels to the device. We forward pass the images through the model to get the logits. We convert the logits to probabilities, and we convert the probabilities to predictions. After the model is evaluated, we again do CUDA synchronization, and we calculate the accuracy. Here, again, we have the accuracy as 76.03, and the evaluation time, the inference time that it took on the entire training set, which is 2023 images, was 4.68 seconds. We log the metrics, and we show the performance. The training accuracy is 85.77, and the testing accuracy is 75.28. The precision for the testing is 80.05, and the recall is 67.39. The high precision shows that the rate of false positives is less, and uh, the number of true predictions are more. The F1 score is 73.18 for the uh, test dataset. Here we can see the training and the testing confusion matrix. We can clearly see that the model is able to distinguish between cats and dogs uh, prominently on the test set and on the training set. This is the GPU performance metric, and this is the output logic and how we are thresholding to see uh, for in which class the uh, image belongs to. Here we can see the loss curve, and we can see that it's reducing over the epochs. And this is the demonstration for the model on a single test image. And just to check the model performance on a new domain image, I've downloaded two images and I'll see how it performs on these unseen images. So it predicts uh, this image as dog with 99.72 confidence. And we'll see one more image. And it predicts this image as a cat with confidence 80.77. Thank you.